Quick question about the homework.
Sure. So,
For the final step where we saw, we said we can use MATLAB.
yeah.
Do you need us to write out any more code other than A/B?
No, that's
No.
fine. You don't even have to provide any code, just because I'm more interested in just set up the problem. But then, just because it's homework and you have access to MATLAB, then you can just solve it on there.
So that looks good.
Perfect. Yeah, that's good. Mhm.
Professor, we're done with everything for the homework, right?
Yes.
Yeah.
Yeah.
I have a quick question.
Sure.
So,
Mhm.
on the last problem that you gave us, that you want to run board from the board.
Yep.
I can't seem to picture it, but is this site fixed?
Uh,
Otherwise,
no, this one's actually free. So this one's fixed up here. So the fixed ones are usually when I have this little triangle and an attached to a wall like this. This one's actually a roller. Yes.
so then the angle's gonna be changing here. This
So
is not fixed.
right. So actually, so for this one, we'll talk about it a bit more today. So because we had that, that row of all zeros and then all zeros. So this geometry is actually unstable. So because there's a roller here, this, when you pull down on it, it's actually going to roll down. So what the new geometry actually is, it's actually really hard to determine. But the way that we're going to do with it is that we're kind of artificially able to fix this.
Okay.
Just so we can solve it.
Okay, all right, yeah, I was just trying to picture it, like, wait, is it moving?
Yeah.
Or is the angle changing?
In reality, it should be moving. It should, the angle should be changing.
All right.
Happy New Year to you too. You're the dragon. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? We're good. Everyone have a good weekend? Everyone watch Super Bowl? Yeah. I had a bunch of friends over my place for Super Bowl, and the way my friends are, they're not that interested in football, so more people came to watch Usher more than anything. But it was great watching Usher. So I don't know how old you guys all are, but I kind of grew up. I had like middle school, high school at the time when Usher was really popular, and so to see him perform the Super Bowl was amazing. It was great. One of my friends actually too. We had a contest because of like, naming Usher songs, and then one of my friends, he's basically like Filipino Usher, so he knows like all of Usher songs by heart. And so we played the intro to Let It Burn, and he could actually recite everything from memory, even the parts when Usher in the beginning is just like talking to an imaginary girlfriend, like he knows that by heart too. So yeah, it was a lot of fun. That was okay. So the plan for today, I wanted to go back to the first thing I want to do today, I wanted to go back to that example from last time, with the roller support, because there's a few more nuances that I wanted to explain about that. And then after that, we're going to move on to beams. And so we're just about done with trusses in terms of everything that we can do with that 1D, 2D problems. And so the next thing is beams, which are kind of a very different type of element. So we'll be getting into that today. We'll be doing a few examples, and then yeah, we'll go from there. Okay, so just a reminder, remember your homework problem set 1 is due on Wednesday night, and so make sure you guys are finishing that up. The 2D problems are quite lengthy, so make sure you are, make sure you're on top of that, and then make sure you submit it before the deadline. So there were a couple typos, and so hopefully everyone got my email today. There were a couple of typos on the solutions for, I think, problem 2C and 3C. So I've since corrected those, and then they're on. I've uploaded the updated PDF on. So and so if you were kind of confused on that, apologies for the confusion, but I think it should all be good. Okay. All right. Any questions I can answer before we get started for today? Okay. Okay, so I did want to go back to the example last time. So actually, let me go through here. There's not much to write down, so I'm just gonna jump back into the notes from last time. Okay. And so let me kind of erase this. There we go. Okay. Okay, so last time, we were doing this example here. Okay. So we have the structure. It's just a 2-bar structure where we had one element that's kind of angled up at a 30-degree angle and another element that's horizontal. Okay. So I use this example for a couple of reasons. So the first main reason that I brought this up was to kind of start a discussion on the conventions for the angles. And so you can see here that, even though the angle that's given in the problem is 30 degrees, that's not the angle that we actually plug in to the element stiffness matrix a lot of the time. And so the angle that you have to plug in is the one that actually makes an angle, or the angle that the element makes with the positive x-axis. So you want to make sure that you're computing your angles correctly. Okay. But the other reason I brought this example up was here in our global stiffness system, right? So after you apply, after you assemble all of the element stiffness matrices, after you apply the boundary conditions, what can happen sometimes, not often, but it does happen, is that if you have a row that's entirely zeros and the corresponding column is entirely zeros as well. And so let me highlight it again, just so you can kind of see, okay? So you can see that this entire last row here is zeros, and this column right here is all zeros as well, okay? All right. So this is a singularity. And so what this basically means is that our structure is not stable, right? And a few people have actually noticed as well. And so if you actually had this structure in reality where you had kind of a fixed support up top, a fixed pin up here, but this one is a roller, right? If you actually pull down on this, right, and so if you actually apply force on the end, or even without a force, even if you just kind of let it fall through its own weight, question due Thursday. Oh, sorry, yes. So the homework is due Thursday. Sorry about that. I'm kind of confusing with another homework assignment that's due Wednesday. Yeah, sorry about that. Yeah, homework's due this Thursday. Yep. Okay. So if you actually make this structure in reality with that roller support, this structure is actually going to be unstable. So it's actually not going to be able to hold this shape, because with this roller support, what's going to happen is that this roller is actually going to start rolling down here, right? And the entire structure is actually going to move, right? And I think last week someone asked a question of, how do you know, what the new geometry is going to be like? Well, that's actually quite hard. And so you actually need to solve that as like a dynamics problem, which we're not equipped to do at the current time, right? And so, we're kind of faced in kind of a difficult situation where we have a linear system here that we can't solve because this structure isn't stable. And we don't know what the actual stable geometry looks like. In this case, I think it's not too hard to figure out, but in kind of the more general case, there's no mathematical way to actually do this. And so in these situations, if you come across a situation, it's actually fair for you to say this is a stupid ass problem and Dr. Trent is crazy, because that's essentially what it is. So I basically gave you an under constraint problem. And so if this is the case, then in order for you to solve this, you need to kind of artificially constrain it more. Okay. And so the way that you do that is that you can actually transform. So you can change one of these supports from a roller support to a fixed support. Okay. All right. And so to do that, I have too many colors going on. It's hard to see. Okay. So to kind of artificially constrain the structure more, you would basically change that last row there, or that last diagonal, to be a 1, okay? And so by changing this to a 1 here, we are artificially constraining the structure. Right, so that's what you would have to do. So only by doing that can you actually solve this system for the deformation in this case. Okay, but the reason I bring this up, I don't have a weird kind of humiliation thing. So I'm not into that stuff. But the reason I bring this up is that this is actually quite a common problem in FEA in general. And so when you're using ANSYS or when you're using any kind of commercial software, your software is going to be checking for if you have enough constraints on the structure. And it's not that uncommon for you to have a situation where you under constrain your simulation as well. And you have question, so F3Y will be 0. Yes, F3Y will also be 0. And so you're gonna be in a situation where you also need to put additional constraints on your structure in order for your simulation to run. Okay. And so the way ANSYS basically tells you this is that ANSYS will tell you that there's something called a solver pivot warning. So that's basically your indication that you need to add more constraints to the structure. Okay. And mathematically, this is essentially why. And so the reason ANSYS gives you that error is because it's creating a linear system here, and it's not able to solve for a solution because it either has a row or there's multiple rows of all zeros, and it's not able to invert the matrix to give you your solution. Okay. And so you either need to go back to your original geometry and try to come up with, where does it make sense to add a fixed constraint or to add more constraints? Or, is there something else wrong? Is there some other issue with the boundary conditions that I need to address? And so there's not a kind of a fix all kind of fix to that. It's really kind of situation dependent, but this does happen quite often in FEA. And this is kind of the mathematical reason kind of why it does that. Okay. So I wanted to bring that up. I'm not going to give you, or I'm going to try not to give you any more problems like this on the homework where you have to artificially constrain it. But in situations like that, that's essentially what you have to do. Okay. All right. Any questions on this? Okay. All right. So let's jump to beams then. And so we're going to talk about the application of beam elements in the direct stiffness method. Okay. Okay. So in a nutshell, beam elements are structural elements that are able to support transverse and rotational deformations. Okay. So what do I mean by transverse and rotational deformations? Okay, so let me go ahead and draw a beam element for you here. Okay. So in a lot of ways, a beam element is kind of opposite of a truss bar, right? A truss bar, if you remember correctly, a truss bar is only capable of axial deformations. Okay, so those are deformations that are parallel to the element itself. Okay, beam elements allow for deformations in basically every other direction, and so transverse deformations. So let me call this D1Y and D2Y. Okay. Transverse deformations are deformations that's in the direction that's perpendicular to the element. Okay. So any kind of bending that's associated with an element that comes from transverse deformations. Okay. On the flip side, rotational deformations we usually indicate with an angle. Okay. So θ1 and θ2. These are the rotational degrees of freedom. And what they indicate is a change of orientation or change of slope of the element at those locations. Okay. So we are now going to be adding these two, sorry, the iPad's a little bit behind. we're now going to be adding these two modes of deformation to our direct stiffness. Okay. So in contrast. Truss elements only allow for axial deformation, okay? So beams are, beams are basically everything else, okay? All right, so with the introduction of beams, this kind of opens up our repertoire quite a bit in terms of, the types of structures that we can analyze. Because with truss structures, for the most part, we're mostly limited to kind of triangular structures, because the structure has to be in a certain way where, most of the forces and most of the deformation is going to be down the barrel of the element. But now that we're introducing transverse deformations, rotational deformations, this kind of opens up the possibilities of the type of structures we can actually do. But it also brings with it a completely different element stiffness matrix. Okay, so that's going to be the focus of this week is how do we or first of all, what's the element stiffness matrix for these beams? How do we incorporate that into our direct stiffness method, and then just doing a few examples to kind of hammer that home. Okay. All right, any questions on this so far? All right, question. So we're not considering twist, right? So I'm guessing you're considering torsion. So we're not. So that would be a three-dimensional effect that we can certainly, that it's possible to do. It's just that it kind of adds just more complexity without much education, if that makes sense. Yeah. Remember, we're only really using the direct stiffness method to kind of introduce the FEA method in general. We're introducing, different types of elements, how that affects the whole method. So torsion definitely is an important effect. It's just I choose not to include it just because it makes the problems kind of more hassle than they're. Yeah. Yep. All right. Any other questions on this? Okay. All right. So let's take a look at the element stiffness matrix for a beam. Okay. All right, so first thing I'll note here is that because for a beam, we're considering both transverse and rotational deformations for two nodes in a beam, that means we're going to have 4 degrees of freedom per beam element. So that is D1Y, theta 1, D2Y, and theta 2. Okay. And so what that means for our element stiffness matrix is that our element stiffness matrix is going to be 4 by 4. Okay. All right. So in particular, it's going to look like this. And so on the one hand, you're going to have the forces, and so you're going to have Fy1. Okay. For the rotational degrees of freedom, we're going to say that instead of a force, we're going to have a torque, okay, or a moment. So it's going to be M1. So our forcing vector looks like Fy1, M1, Fy2, M2. Okay. This is going to be equal to our element stiffness matrix, which is yet to be determined, and then dy1, theta 1, dy2, theta 2. All right, question. Don't we consider axial deformation in beams? And so for now, we're going to ignore the axial deformation. We are going to bring it back. And so the next topic after this is going to be frame elements. And so frame elements is going to consider axial deformation, transverse deformation, and rotational deformation all at once. But those problems are massive because with that, you'll have 6 degrees of freedom per element, and then so your element stiffness matrix is going to be 6 by 6, and so it gets quite nasty. But for now, we're going to ignore the axial deformations. Yeah. Okay. So now the question is, how what are we going to put inside this element stiffness matrix? All right, so this is something I'm going to largely skip, and so I'm not going to give you the full details of this derivation. It is in the lecture notes, and so if you are interested, you can definitely check it out there. But in a nutshell, we're basically going to be using the Euler-Bernoulli beam equation. And so what we basically do is we apply it onto a beam element with two nodes, okay? And we apply it with a certain deformation field. And so if you apply that and you go through the derivation, and that will give you your element stiffness matrix. Not in the deformation, in the derivation. That derivation. Okay. So the nature of this derivation is a little bit different than how we derive the element stiffness matrix for a spring and for a truss. This one actually utilizes the differential equation for a beam quite a bit. But just for the sake of time, I do want to make sure I get to some examples today. I'm going to largely skip it. Okay. And so I'm just going to give it to you. And so the element stiffness matrix for a beam looks like the following. So Fy1, M1, Fy2, M2 is equal to. So in front here, we have a factor that multiplies the whole thing. So we have EI over L cubed. Okay. This is multiplied by a 4x4 matrix. And so this is going to be 12, 6L minus 12, 6L. Okay. That's the first row in the matrix. So our same rules from before actually apply here too. So all element stiffness matrices are symmetric. And so as soon as you write the first row, you can take that first row and write it into the first column as well. So let me go ahead and do that. So our first column here is going to be 12 up top, then 6L minus 12, and 6L. Okay. Next row, we already have the first entry, which is 6L. The diagonal entry is 4L squared, and minus 6L, 2L squared. Let me do the same thing and write those entries into the second column. Okay. All right, in the third row here, we have a 12 minus 6L. Okay. Once again, we're gonna rotate that down, so we have a minus 6L in the fourth row in the third column. And then the very last entry is gonna be 4L squared. And of course, this is multiplied by the deformation vector d1y, theta 1, d2y, theta 2. Okay. So that's the element stiffness matrix for a B. Any questions on this so far? Okay. So before we jump into an example, let's talk about constraints a little bit more, or boundary conditions. Okay. So with the last example that we did with trusses, we were introduced to the concept of a roller support versus a pin support. Okay. We're going to expand on that a little bit more because now we have a rotational degree of freedom. Okay. So we need to talk about, how the different constraints affect that rotational degree of freedom, as well as the translational ones. Okay? So there are three types of constraints. And honestly, the difference between some of these is not going to be relevant until we get to frame elements, which is the next thing. Okay. All right. So the first type of support that we have here is called a fixed support, okay, or fixed constraint. Right. So visually, what it looks like is that you have a beam, and that's literally kind of just stuck inside a wall, right? And so you have a wall that's basically attached to that. Okay. So the fixed constraint refers to this end right here on the left, right? We have the beam kind of stuck inside the wall. And so this is the most powerful type of constraint. And so all degrees of freedom are constrained here. And so we have dx is equal to 0, dy is equal to 0, as well as theta is equal to 0 as well. Okay. So it allows no degrees of translation and no degree of rotation. All right, so next is the constraint that we've been mostly using in our truss problems. So I think in the past I've called this a fixed constraint. Well, for trusses, it effectively is a fixed constraint. But I want to make the distinction between this and a true fixed constraint, which is on the left. Okay. So whenever you have that little triangle symbol and that triangle is kind of directly attached to the element, and that triangle is kind of fixed to the ground, this is something called a pin constraint. And so a pin constraint is going to constrain the deformation. So we're going to have dx is equal to dy is equal to 0. Okay. But the pin constraint is not going to constrain any of the rotations. We're going to have theta be free here. Okay. So at a pin constraint, the structure is free to rotate however it pleases. Okay, and so the last type of constraint, this is the one that we talked about last time, is a roller. Okay. And so a roller constraint visually looks like this. Okay. So it's going to be basically look like a roller skate. So it's going to be basically a constraint with wheels, and the wheels are going to be on on a wall or something like that. Okay. And so in these types of situation, usually only one dimension of the deformation is fixed. Okay. And so in this case, the dy is fixed, okay? Because that roller is going to prevent any kind of deformation in the y direction. But because of the roller, it is free to translate in the x direction. And it is free to rotate as well. Okay? So both dx and theta are free in this case. So people always ask me, with the roller as I typically draw it here, it makes sense that it would constrain any deformation in the negative y direction, right? Because there's a wall right there. But because it's wheels, technically, you can kind of just lift it up and kind of just take it off that way, right? So there technically shouldn't be any resistance in that direction as well. But usually when you have a roller support here, the way I like to think about it is that the roller is inside a track. And so that track kind of prevents any kind of upward motion as well. And so, in this case, dy is completely constrained. Okay.
Shouldn't that make the angle 0 also?
No, it's free to rotate as well because the beam here is still pinned right here. And so the beam is free to kind of rotate up and down this way. Yeah. The track is only there just to prevent any kind of y deformation. Yeah. Mm-hmm. All right. Any other questions on this? Okay. So this will become a lot more relevant when we do frame elements, but I thought this would be a good chance to introduce this here. Okay, so let's do a fairly simple example, just to kind of see how all of this kind of fits together. Okay, so let's consider this 2-element beam. All right, so on one end, we're going to have a fixed support. And on the other end, we're going to have a pin support. Okay, so we'll call this element A. We'll call this one element B. You have node 1 attached to the wall, node 2 in the middle between the two elements, and node 3 that's on the end. Okay. All right. So we're going to do this one just purely symbolically. So I'm not going to give you any numbers for this, but it's just to kind of show you how all the matrices are set up. Okay. All right, so let's assume that E and I are constant throughout. So we don't change any material and we don't change the cross-sectional area, okay? Cross-sectional shape. I wrote something down, I promise. It's the iPad that's crapping out. Okay. Oh, I should have mentioned this earlier, but I always forget to do that every year. But in the element stiffness matrix for a beam, the capital I that's there, that is the moment of inertia. So that's the moment of inertia of the beam cross section. Okay. So we have E and I constant throughout the beam, and we're going to consider these as pure beam elements. And so we're going to ignore any axial deformation. Okay. All right, so let's talk loads. And so we have two loads being applied here. And so we have a downward load, a downward force of P being applied on node 2. Okay. And we also have a counterclockwise moment or counterclockwise torque of M being applied on node 2 as well. Okay, so in this case, we're not given any numbers. We're just gonna do this all symbolically. And so for this one, all we're gonna do is we're gonna assemble the global linear system and apply boundary conditions. Okay. All right, so it's a pretty straightforward direct stiffness problem. We only have two elements here. So we're just gonna kind of run through the motions pretty quickly. Okay. Any questions on just the setup for the problem? Okay, all right, so let's go ahead and go through it. All right, so the first thing we need to do as part of the direct stiffness method is to write out the element stiffness matrices. All right, so we have the element stiffness matrix for element A. So since we're not given any numbers and we're given all of the properties here symbolically, I'm just going to write it down here. So for Ka, we have an EI over L cubed multiplied by 12, 6L minus 12, 6L. Write that into the column. 4L squared. And then third row, you have 12 minus 6L. And since element A here is connected to nodes 1 and 2, we have D1y, theta 1, D2y, and theta 2. Okay, now we have element B. Okay, so element B, we have the same thing. So we have EI over L cubed. Its properties are identical to element A, so we're just going to copy this straight over. The only difference with element B is that it's connected to nodes 2 and 3. So it's going to be D2y, theta 2, D3y, and theta. All right. But the contents of the matrix are the same, which makes it boring, but we're just this is kind of just our first try at it. Okay. All right. So now that we've written out the element stiffness matrices, the next step is to assemble. Okay. So let's go ahead and do that. So since we have 3 nodes here and each node has 2 degrees of freedom, that means our global stiffness system is going to be 6 by 6. Okay. All right. So let me write in the forcing vector first, since we have F1y, M1, F2y, M2, F3y, and M3. Okay. Oh, let me Let me add in our factor in front here. So we have the EI over L cubed. Okay. All right, so now we need 6 columns here. So we have a D1Y column, theta 1, D2Y, 2, D3Y, theta 3. Y, 1. All right, so this one's pretty straightforward. We're just gonna enter these in here, right? All of these elements are contiguous with each other. So this is gonna be element A. Blue. B. So we only have a little bit of overlap. So we only have a little bit of overlap in that 2x2 segment in the middle. So let me just go ahead and write everything in. This part's pretty straightforward here. You have 12, 6L, minus 12, 6L. L squared minus 6L. Okay. All right, now we have the overlap region. It's the overlap region. We're going to have some things cancel out. And we have some things that add together. So we can have a 24, 0, 0, and then 8L squared. Okay. So that's what you get when you overlap kind of the bottom right-hand corner of the stiffness matrix, the upper left-hand corner of the other one. Okay. And then everything else here is going to be the same as up there. So you have minus 12, 6L. Okay, and then of course, everything that's not in a box, we're just going to put a 0 there. As always, there's a lot to write down. But then as you start to do more of these, you kind of start to get into a rhythm of doing these things. All right. All right, so everything we've done up to this point has been pretty standard. So that's just our standard direct stiffness method. The only caveat, of course, is that we're using beam elements now. So with the different element stiffness matrix. Here's where the wrinkle gets a little bit interesting. So let's add our boundary conditions here. All right, so if we go back to the diagram for this problem, we can see from the diagram here that we have a fixed support on node 1. Whereas on the right, we have a pin constraint on node 3. Okay. And I write really fast. I should stop that. It's been 4 weeks of me making jokes about the bad Wi-Fi thing. Yeah. I know they're not funny. All right. So what does this mean? So that means the degrees. So let's look back at our cheat sheet here in terms of how this affects our degrees of freedom, right? Remember, we're only considering beam deformation. So we're only considering transverse deformation and rotation. Okay? So on the left-hand side for the fixed constraint, this is pretty easy. So a fixed constraint is going to eliminate absolutely everything. So this means that d1y and theta 1 are both 0. Okay. Whereas for the pin constraint is gonna restrict the deformations. We have d3y, and d3y is gonna be 0. Okay. But theta 3 is gonna be free. Okay. And remember, what free basically means is that we're gonna leave that entry in we're gonna leave that row in the matrix unloaded. So we're not gonna make any changes there. Okay. But we are gonna make changes to the d3 row, and we're gonna make changes to the d1, y, and theta 1 row. Okay. Okay. So let's go ahead and make those changes to our matrix here. So first, let's apply the fixed constraint on node 1. Okay. So that means this entire row, the first row, needs to be changed. Okay. The second row, which corresponds to theta 1, also needs to be changed. Okay. So let me go ahead and do that right now. So remember, for constraints, we change every entry in the row to zeros except for the diagonal. Okay. So for the first row, it's going to be 1, 0, 0, 0, 0, 0. And for the second row, we're going to put the 1 on the second column. So we have 0, 1, 0, 0, 0, 0. Okay. And then similarly, we're going to put a zeros out here. So F1y is 0 and M1 is 0 as well. Okay. That's good. Now let's do the pin constraint on node 3. And so pin constraint means that d3y is going to be 0. That means we need to change this entire row right here. Okay. But theta 3 is going to be free. So the very last row in the matrix here, we're actually going to leave it alone, right? We're not going to make any changes to that row. Okay, so this last row here, or this second to last row, is going to be 0 in the forcing vector. 0, 0, 0, 0, 1, 0. Okay, now let's apply the forces. And so we have a force of P being applied on node 2 in the downward direction. So that means F2y is going to be a minus P. Okay. And we also have a counterclockwise moment of M being applied on node 2 as well. So that means M2, we're going to place that with M. Okay. Okay. And of course, the last thing we have to fill in here is M3. M3 is just any kind of load or rotational load or torque or moment being applied on node 3. We don't have any of that. And so we're just going to turn this M3 into a 0. Okay. All right, so that's beams. And so, there's really not much to it. You have to kind of change your frame of reference a little bit because, the deformations are in different directions. And so that means our element stiffness matrix is going to be different. But besides that, we're following the same process as before. Okay. Element stiffness matrix, assembly, boundary conditions. And then if you have numbers and if you have access to a computer, you can solve it. But if not, just, up to this point, it's just fine. All right, any questions on this? Okay. All right, so before we do the next example, I do want to go over something, which is how to compute reaction forces from these direct stiffness solutions. Okay. So what do I mean by reaction forces? Well, it's not explicitly stated in the problem, but all of the problems that we're considering here are static situations, right? Okay. And when you have a static situation, that means if you were to sum up the total number of forces and the total number of torques in each direction, they would all have to sum up to 0. Okay. So what that means is that when we have a structure like we have, and we're applying external forces on it, there actually are additional forces being applied to make sure that we reach static equilibrium. Okay. Where these forces come from, they actually come from the constraints. And so the forces that are applied on the constraints that are needed to achieve static equilibrium, we call those reaction forces. Okay. So even though it's not explicitly stated, and even though it's not, we didn't actually compute it, but the fixed support and the pin support in the previous example, those supports or those constraints are applying forces onto our structure to balance out the external forces. Okay. All right. And sometimes this is useful. Sometimes you actually want to compute these reaction forces, because often these reaction forces can tell you, if your structure is being held up by certain constraints, which constraints are most vulnerable to failing. And the lucky thing is that we can actually compute these from our direct stiffness solutions. Okay. Okay. So to compute the reaction forces in any direct stiffness situation, what you need to do is you need to this can only be done after you solve for the deformation solution. Okay. So after you compute the deformation solution, what you need to do is you need to multiply it by your global linear system, the one that you had before you applied the boundary conditions. Okay. All right, so basically at the end of step 2, so after you do the element stiffness matrices and after you assemble them all together, that's the global linear system that I'm talking about. Okay, so the one you had before you applied the boundary conditions, if you multiply that by your deformation solution, you're going to get a vector of all the reaction forces. Okay, and we'll talk about that in the next example. All right, are there any questions on this before we jump into that example? Okay, all right, let's do one last example for today before we wrap it up. Okay. This example is interesting too because it incorporates a spring. Okay. Okay, let's consider again a 2-element beam. So it's going to look very similar to the one we did on the geometry of the last example, except on the right, we're going to replace the pin support with a spring. Okay, so we have our 2-element beam here. So we have elements A and B. Okay. The left side of element A is fixed into the wall, just like before. Okay, so we have node 1, node 2, node 3. Okay. And on the right side here, we're going to have a beam that's supporting this. And so this beam here is going to be an additional element. Okay, so we'll call that element C. All right, so let's get some properties here. And I actually have some numbers for you this time so you can visualize it. Okay. So each of these beams we're going to say has a length of 3 meters. Some of the other parameters for the problem, we have the Young's modulus for the beams. The Young's modulus for the beams is 210 gigapascal. Okay. The moment of inertia of the cross section is going to be 2 times 10 to the minus 4 meters to the 4th. Okay. And our spring constant for our spring, so this is the spring constant for element C. This is going to be 200 kilonewtons per meter. Okay. And for the loads, all right, question. Rotational deformations will result in orientations of the element different from what we have for the problem. Won't that cause errors in the solution compared to the actual equilibrium? That's a great observation. So yes. So the question is, when we solve these systems for the rotation and technically for the deformation as well, the geometry for the structure will change, right? And so for the case of rotational deformation, that's going to change the orientation of the element at that node. So one assumption that we're making here that I should have been more clear from before is that we are using kind of the linear elasticity assumption, which means that we're assuming that all the deformations and all the rotations that we compute are small relative to the element itself. So we are computing deformations and rotations as well, but compared to the overall size of these elements and the overall shape, they're relatively small. And so we're going to assume that in the grand scheme of things, the geometry is relatively unchanged, even though we're computing these deformations and rotations at the nodes. Yeah, that was a good question. So basically the errors will be small as well. Yes. Yeah. So we're basically assuming that the errors will be small relative to everything. Yeah. Okay. And so for the forces, we have a downward force applied on node 3. And so this has a magnitude of 50 kilonewtons. Okay. The question, so does this problem have 3 or 4 nodes since the spring is connected to the ground? Good observation too. So technically this does have a 4th node here. We can include it for now, but because it is fixed to the ground, you know, that row is going to zero out anyway. And so you know, this would be a situation where, you know, I think it's okay to not include it. Although that also means that you're cutting your spring in half. But I'll show you what I mean. So we'll, let's include it for now. So let's include node 4 attached to the ground. And then when we assemble it, I'll kind of show you what I mean when you can just kind of just cut it off. Yeah. Okay. And so for this problem, let's use the direct stiffness method to compute. Let's compute the deformations at each node of the system. Okay. Oh, and then afterwards, we're also going to compute the reaction forces. So I guess actually let's include the ground here because we need to compute the reaction forces here. So that means we're going to compute the reaction forces at node 1 and at node 4, because node 4 is going to have reaction forces as well. Okay. All right, but that's the last thing that we're going to do. Okay, so let's go through our direct stiffness methodology here. So let's start with the element stiffness matrices. Okay. So let's start with the two beams. So I'm going to start doing these symbolically just because, you know, plugging in the numbers now is you can do it. You can plug in the numbers now if you want, but it's you know, it's usually a little bit easier to kind of do it at the end. Okay. So for element A, we have EI over L cubed. And we have our usual spring beam element stiffness matrix. So that's 12, 6L minus 12, 6L, 6L minus 12, 6L, 4L squared minus 6L, 2L squared. And then element A here, of course, is connected to nodes 1 and 2. So we have D1Y, theta 1, D2Y, theta 2. Okay. Okay. KB is going to be identical. It has identical properties as a beam A. The only difference here is that element B is connected to nodes 2 and 3. So you have EI, L cubed, 12, 6L, minus 12, 6L. Okay, so we wrote those pretty quickly. So element B connected to nodes 2 and 3. Okay. The same entries as KA. All right. And then we have the element stiffness matrix of element C. So element C is our spring. So technically speaking, you know, if you look at the spring here, it's a vertical spring. And so you can easily do this with a 2D truss system. Okay. And so you can treat this as kind of a two-dimensional spring where we rotate it up 90 degrees. Okay. right? And so you can have your 4x4, 2D spring element stiffness matrix here. Or, one thing that you can notice is that the spring, we know the spring is limited to just expansion and contraction, right? And so the spring can only in this case, can only deform in the Y direction, right? That just so happens to align with the transverse deformation of element B, okay? So let me write that down. So the axial okay. So the axial deformation of spring C perfectly aligns with the transverse deformation of element B. Okay. And so what does this mean? Okay. That means when the spring C, let's say it expands, right? When it expands, that deformation is going to align perfectly with the transverse deformation of the beam. Okay. So this lets us simplify our element stiffness matrix. And so instead of doing a 4x4 for a perfectly 2D one, let me write our typical 1D spring element stiffness matrix. And so that is our 2x2 K minus K minus K, K. Okay. And then for the degrees of freedom here, we're going to have D3Y and D4Y. Okay. So we're going to save ourselves some writing and not even consider D3X and D4X. Okay. Because there's in this case, there's no way for us to achieve those deformations because technically speaking, if we were to do this by the books, if we were to do this as a 2D spring, we'd have to include D3X and D4X, right? And that's what gives us our 4x4 element stiffness matrix. But if we think about it, this spring can only go up and down, and the beam B can only go up and down and rotate as well. And so there's no way, with the elements that we've chosen for this structure, there's no way to actually obtain a deformation in the X direction. And so we can just kind of cut that out completely and just use our 2x2 1D element stiffness matrix just to save us some light. Okay. If you did treat this as a 2D element and you did include D3X and D4X, that's perfectly fine. You're still going to get the same result. It's just going to take you a bit more right. All right. Any questions on how we obtained these? Okay. So let's assemble. I don't think we'll have time to finish up everything today because I want to make sure I talk about the results. But let's assemble the global system first. Okay, so let's work on assembly here. Okay. We have quite a unique system here because we technically have 4 nodes, right? But node 4 is only connected to a spring, right? So that means node 4 okay, because node 4 here is not connected to a beam, there's no need for us to include a row for theta 4. Okay. So there's no need for theta 4 row. Okay. So that means our global system, we're gonna have nodes 1, 2, and 3. Nodes 1, 2, and 3 are gonna have transverse deformation as well as rotation. Okay, so that gives us 6 degrees of freedom. And then node 4 only has d4y. So that means our global stiffness system here is actually gonna be 7 by 7. Okay. All right, so let's go ahead and write all those down. So you have F1y, theta 1, F2y, theta 2, F3y, theta 3, and then F4y. 7 roots. All right. And then for columns, we have D1y, theta 1, D2y, theta 2, D3y, theta 3, D4y. Question.
Yeah.
Oh, yes, yes, sorry about that. Thank you. My mind is thinking about my dinner already. Yeah. You guys get the bad end of the straw because I do a lecture right before this. And I have to eat a really early lunch because I have a lecture right around midday, and so I'm always like starving by the end of this lecture. So if I make mistakes or if I seem dead, definitely call me up. There's nothing like a little bit of shame and embarrassment to whip you into shape temporarily. Okay, so let's go ahead and assemble our matrix here. Okay. Just like we did on the first example today, we're gonna put in our factor here. Okay. So we have 2 beams, and so we need to have our EI over L cubed out in front. Okay. That's gonna save us a little bit of writing. Okay, so let's start with element A. Okay. Element A is connected to nodes 1 and 2. Okay. So it's gonna be that upper left portion right there. Next, we have element B. Okay. Element B is connected to nodes 2 and 3, and so that's going to be this portion right here. And then we have element C. Element C is the interesting one. Okay. So element C is our spring. Okay. So it is connected to nodes 2 and 3, but remember, a spring does not support any rotation. Okay. And so that means the places that we insert it are going to be here, D3y, 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 D4y. Okay. So both the cross terms. And then D4y, D4y. Okay. All those squares should be the same size. You make it so. Okay. All right, so make sure you skip the theta 3 because the spring cannot support any rotation. Okay, so let's add these in. So let's start with element A. So for our spring element A, we have 12, 6L minus 12, 6L. Same thing into the column. For the overlap portion, I'm just going to write that one in. This is the same as our first example. So we have a 24, 0, 0, 8L squared. Okay. All right, now we have all the entries for element B. So we have a minus 12, 6L, minus 12, 6L, minus 6L, 2L squared. I'm going to save the overlap portion for a bit, but I'm going to do everything around the overlap. Okay. Actually, I'll write in the first part, because the first part is fine. Okay. And so the last thing here is we have to add in our spring. Okay, so our spring just consists of the spring constant K, right? So it's tempting to just come in here and just write, K, right? So minus K, K, and plus K, right? It's tempting to do that because that's what we've always done. But remember, in doing the springs or doing the beams, we have this factor out in front right here as well, right? So the implication here is that EI over L cubed is multiplying everything inside the matrix, okay? And so if we want those entries there to be just K, we have to factor in this thing out in front. And so we actually multiply the K by the inverse of that. And so instead of just K, we're gonna have plus K times L cubed divided by EI, okay? And so all these entries here are gonna have L cubed divided by EI. Okay, that's just to make sure that the units and everything is consistent with the original element stiffness matrices. Okay. All right, any final questions on this before we wrap it up for today? Okay, all right, so we'll pick this up on Thursday. I'll go over that spring constant thing one more time. That's just to make the units consistent, but we'll pick it up with that. We'll finish up this problem. We'll apply the boundary conditions. We'll get our solution, and then we'll compute the reaction forces. All right, so thank you guys for coming today. I hope you guys enjoy the rest of your day. Hope you guys enjoy your evening, and I will see you on Thursday. Thanks, guys. Hey, Dominic, see you guys. See ya, you too. See ya, have a good night.